Now let me show you an example, which is a little bit, it's very good technology, but it's slightly problematic in terms of measurements. So this example was actually following a different idea of getting very high Q resonators by essentially using miniaturized cavities. We will see more examples if we have time in this class of miniaturized cavities, but essentially these are substrate integrated cavities. So you basically take a substrate, it was silicon in this case, but it can work with any substrate. It was etched and then it was metallized. So this is actually gold right here. And then there's another wafer on top that basically comes and seals and creates a cavity. You can see here, this is the input and the output coupling. And this was an example where John Papapolymerou, that was doing this, was trying to measure the unloaded quality factor. So he excited this miniaturized cavity through a microstrip line, and you can see a little aperture coupling here. So this is essentially a hole that allows waves to get into the cavity. So this is essentially a magnetic field coupling from here and here. This is the input magnetic field coupling, the output magnetic field coupling. Now the results are very good. This is a very high quality resonator. This is essentially the measurement of this. But as I mentioned before, the suboptimal thing that was done here is that the coupling was too strong. So if you will see the S21 here is actually practically at the 0 dB level because it's a very high quality resonator. And John, had other reasons to expect a high Q here. For example, simulations agree with measurements, so this was a good indication. But his measurement improvement would have become better. Sorry, his measurement accuracy would have improved if this coupling had been much, much weaker, which is what I advise you to do in the previous section. Nevertheless, he measured the quality factor in the order of 500, which again is a heroic result, particularly at the time this was published. Now, they extended this even further by now making filters. And this was done by Lee Harley. And this is another heroic example, basically, of coupling this kind of cavities. Now, once you see this layout here, or this schematic rather, again, you can very quickly guess what's happening. So first of all, how many poles we have, how many resonators we have? 3. There are 3 cavities right here. So this is a third order filter. You can see very clearly the magnetic field for the input. So this realizes the M01. You can see the interresonator couplings. So this guy here will realize the M12. This is realizing the M23. This is realizing the M3 load. And then what is a little bit difficult to appreciate from this schematic, if you have never done this type of work, is the complexity of this fabrication. This is essentially a fabrication that has to basically bond, count how many wafers, 500 micron silicon wafer for the cavity, 100 micron wafer for the slot, the coupling slot, and then the whole thing repeats again. I can't tell you, I actually overlap with Lee in grad school a little bit. I can't tell you how many tries it took to actually make this thing work, of successfully bonding these wafers and actually getting the couplings that you want. I'm going to skip this result, but let's go to the performance. This is essentially the measured versus the simulated filter response. It's more or less what you expect. It has a fantastically good insertion loss because the quality factor is actually very high. But I also want to show you what I mentioned before. Look at, for example, this unwanted mode, and look at this unwanted mode. So there was actually a surface wave launched very close to the passband. Lee was very fortunate to not have this right in her passband, which is, of course, right here. But if she did have it, it would have been difficult to actually extract anything. So that shows you, again, the danger of exciting unwanted modes. And then very quickly, she came up with even better fabrication technology, where now instead of stacking cavities vertically, she was able to basically stack them horizontally. So again, this is a 2-pole filter, 2 cavities filter, but now the interresonator coupling is this aperture here, which is, again, you can see it right here. This is, again, the external coupling between the resonators and the source and the load. And she calculated everything for this to be a 2 second-order Chebyshev filter, and then she mapped all the coupling coefficients that you guys know how to calculate now to physical realizations. I will skip the fabrication details. I'll skip the measurement results. Just want to show you one more example of her fabrication success. This was essentially a fourth order filter. Now there are essentially 4 cavities, and there is a cross-coupling section between the first and the fourth resonator. So my point through all of this is that now you have enough knowledge to simply understand what things are doing literally just by inspection. And that's my point, is that the math is good and you should be able to do it, but those should lead eventually to some intuition, and that's what I'm trying to encourage you to do. That's the measurement result.